Some of the most exciting developments in cutting-edge physics are taking place here in the UK. These include the world's most powerful lasers, particle accelerators, the development of renewable energy through fusion, new advances in plastic electronics, creating robots to investigate other planets, and exploring the universe using the latest technology in space science. Physics today provides us with a way of looking at the universe we live in. It covers everything from the nature of what we are made of to the size of the universe.
In this film, I'll be taking you on a journey to some of the most exciting cutting-edge physics in the UK and showing you some demos that will captivate the minds of students. By accelerating charged particles like protons and colliding them together, physicists can gain new insights into the origin of the universe. At CERN in Geneva, the hunt is currently on for the Higgs boson, a particle that physicists think is linked to the origin of all the mass in the universe. If we find the Higgs boson, we'll have the greatest insight ever into what the universe was like close to the Big Bang. But there's also a possibility that we won't find it, which in a way is more exciting because it means we'll have to go back to the drawing board and start again with completely new theories.
Particle accelerators are not only used for smashing atoms, they're also used for a whole range of applications, and they've thrown up some amazing discoveries. In South Oxfordshire, there's a particle accelerator known as the Diamond Light Source, which creates very intense beams of light that are being used in new and exciting ways. This includes studying the structure of matter at the level of molecules and atoms.
Diamond Light Source looks like a huge silver donut, and it is the size of about 5 football pitches. This facility was built in order to generate very intense beams of light. And by light, I mean anything from infrared or heat through to X-rays that might be used in medical imaging.
The Diamond Light Source, or synchrotron, is made up of 3 components: the linear accelerator, the booster, and the storage ring. Electrons start their journey in the linear accelerator. They are then transferred to the booster synchrotron, where they're accelerated to very high speeds in a vacuum similar to that in deep space. In the booster, they gain energy. When they're nearly at the speed of light, they're injected into the storage ring, over 0.5 kilometre in circumference. The electrons circulate and pass through specially designed magnets called insertion devices. As the charged particles travel around the accelerator, they produce very bright light, X-ray beams millions of times brighter than conventional sunlight and finer than a human hair. The X-rays pass through experimental stations where they are focused and filtered to generate detailed analysis of any solid, liquid or gas being studied.
Diamond is a great place to come to if you want to be a world-class physicist and apply your skills to as yet unknown problems. There is a large community looking at the structure of proteins and viruses. They wish to understand viruses, they wish to understand proteins in order to understand their function and, if possible, to find cures for particular diseases.
This picture here is a diffraction image. That happens when we put a crystal of a protein or a DNA or a macromolecule into a beam of monochromatic X-rays.
Essentially, this data here contains information about the whole of the structure of the object you're looking at.
That's true.
And then from that we can generate this picture here. Now, tell me what I'm looking at here.
So what we're seeing in blue is a representative of the actual density of the electrons in a protein molecule. So into this chicken wire, if you like, we fit, this is a trace of the atoms within a protein.
Right.
So it gives us ability to develop new treatments for making sure the proteins stop working in your body, for example.
In other words, an antibiotic.
A novel antibiotic.
The particle accelerator at Diamond has produced some remarkable discoveries, and it's not just physics that will benefit from the electromagnetic rays that it produces.
We can demonstrate how a linear particle accelerator works using one of these. This is a Gauss gun, but instead of accelerating charged particles like protons, it's going to be used to accelerate these steel ball bearings. So there's a long track here, and I've got a very strong rare earth magnet wedged into the track here with 2 steel ball bearings on the other side. I'm going to put my safety glasses on just because the magnets can be a bit brittle. I don't want shards of it going into my eyes. And as I roll this ball bearing into the Gauss gun, the potential energy from the magnet will attract it, and that energy will be converted into kinetic energy, which will be transferred through all of these metal objects and should fire off this end ball bearing at an accelerated speed. So let's have a look. Now, of course, in a real particle accelerator, they wouldn't only use one magnet. There are a series of magnets within the accelerator. So I'm going to put another magnet in just here. We should be able to see that we get a greater acceleration. So let's have a look at that one. Okay, so we got a little bit faster there. Now I've actually got 4 of these, so I'm going to put them all into the Gauss gun now, and we should be able to reach our maximum speed. And just for fun, I've got a few little skittles here, so let me line these up, and I'm going to see if I can knock these over. Right, let's see. So the magnets have accelerated our ball bearings here, just as they'd accelerate charged particles in a real particle accelerator. Lasers are one of the most important technologies to have developed over the last 50 years, and they feature across so many aspects of our lives. One exciting development is using lasers to produce affordable, sustainable energy, fusion energy, using the very same process that powers the sun.
The Central Laser Facility, part of the Rutherford Appleton Labs in Didcot, is home to the most powerful high-intensity focused laser in the world, the Vulcan laser. It creates fusion by heating matter to 100 million degrees Celsius. That's hotter than the surface of the sun.
The kind of way it works is you take a sphere of 2 isotopes of hydrogen, and we compress that with lasers, and we basically compress it to 1,000 times solid density. And what that does is move all the atoms much closer together. Then you need some kind of spark plug. So this is kind of like a nuclear petrol engine, right? So you do the compression, then you need to ignite the fuel. And so you take a really intense laser like the one we have here, a beam of something like 5 microns, which is a fraction of a human hair. So essentially what that's like is taking all the light that's falling from the sun on Earth and focusing it on the head of a pin and fire it in. And that produces hot particles, and those hot particles travel into the dense fuel and will raise it to the 100 million degrees centigrade. Now, obviously, we don't have all the sort of compression lasers or the general size of laser you need to get it to work. But what we can do in here is understand the spark plug physics. So what we do is we take our super intense laser, focus it onto pieces of material, and understand how those hot particles are generated and then how they deposit their energy.
The laser pulse concentrates approximately 10,000 times the power in the UK national grid onto a tiny spot, and in doing so, a very large amount of fusion energy will be triggered.
We are actually right now on the crux of demonstrating fusion by lasers in the laboratory, and once that very fact has happened, then hopefully we will hit the ground running. And for me, that's why it's so exciting. You know, it's a vindication of all the work we've been doing over the last 10, 20 years. So yeah, it's a good time right now.
It's hoped that in 30 years' time, the development of laser fusion will produce enough electricity to power most of our energy needs.
But that's not all. As well as using lasers, we can also release energy from fusion in a magnetically confined plasma. Plasma is the 4th state of matter. We're already familiar with the other 3, solids, liquids and gases. But if we take a gas and give it more energy, or heat it up, then the electrons that surround the nuclei of the atoms in the gas have enough energy to escape. So what we end up with inside our plasma are 2 species, a species of negatively charged electrons and a species of positively charged nuclei. And it's in this type of plasma that fusion can take place. We can have a look at some plasma inside this plasma tube. The first thing I need to do is remove some of the air that's inside here. Plasma has a lot of energy, so it takes up less space than a gas might. Rather than creating the plasma by heating it up, as we might see in a flame or something like that, we're actually going to create this plasma by passing a voltage across the tube. So as we turn it on, we should see the plasma appear. There it is. So could we turn the lights down, please? Now, when we have fusion going, we produce lots and lots of heat, and the plasma needs to be very hot to get that to happen. Obviously, there isn't any fusion going on right here, right now, but we need to keep the plasma away from the walls of the vessel that it's held in, and we do that using magnets. So if I bring my magnet up close to this plasma, you can see how it's possible to manipulate the plasma, move it around using this magnetic field, because the charged particles respond to the magnetic field. And when we talk about magnetically confined plasma, that's really all we mean, holding the plasma in place using a magnet. This technique of using magnetic fields to manipulate charged particles has been used to create the world's largest fusion experiment in the heart of the Oxfordshire countryside.
Scientists at JET, the Joint European Torus, are working together to develop an energy source that replicates the sun.
What we create here is essentially the hottest place in the universe. The plasma we see here is 150 million degrees, 10 times hotter than our sun, hotter than any star in the universe. And we're trying to create that to make electricity for the future, so it's an amazing place to be.
The machines used to do this are called tokamaks.
A tokamak is a device in which we want to make our own miniature sun and to replicate fusion here. In order to do that, we have to contain it in a vessel, and the vessel has to be a vacuum vessel, all the air pumped out for us to put our hydrogen in. And we then have to do what gravity does on the sun, which is hold the sun in one place and hold it all together. We have to do that with another method here. And we use very powerful magnetic fields. And we can see that very clearly here on this playback of a jet plasma, that the magnetic fields are pushing the plasma away from the walls, enabling us to heat it to these ridiculous temperatures.
And the tokamak is actually buried within the equipment, so there's a lot of diagnostics and electronics. This is one of the heating systems, so there's little tiny plasmas which are accelerated, neutralized, and then injected into the plasma to actually heat the plasma inside to 150 million degrees. So besides having the vacuum vessel in the middle, we need all of this equipment to run a fusion device. So yes, it becomes quite big.
One of the physics challenges we have with this plasma, as you can see here, is clearly wobbling here at the edges. It's quite similar to solar flares and sunspots and turbulence on the surface of the sun. Its activity we want to stabilise as much as possible, because the more stable our plasma is, the more easily and more routinely it will fuse and give us lots of energy out. So a lot of the physics has been in studying how we can stabilise and control the plasma to the best possible degree.
What you need to create fusion are two isotopes of hydrogen, deuterium and tritium. But JET only needs to take the amount of fuel equal in mass to a postage stamp.